Hello and welcome to MT3. We are now on eigenvalues and eigenvectors in practice. So basically it's given a matrix, how do you compute the eigenvectors and eigenvalues? Now this is stuff which is discussed in Riley, Hobson and Ben's 8.14, and I require you to read this in parallel with this recording. Alright, so here's the statement of the problem. We've got an eigenvalue problem, matrix A, which is an n by n square matrix. Times a vector x is equal to lambda times x. And the question is, how do we find the eigenvectors x? Now, in general, there will be more than one of these, and the corresponding eigenvalues. Now, just to remind you of our notation, when we have more than one of these x and lambdas, we will write it in this equation in this form. So we'll index the eigenvectors with the I and the eigenvalues with the subscript I. So this equation then takes this form. All right. Okay, so how do we go about solving this equation? And the procedure, it works as follows. Let's first of all write this as we have a matrix here multiplying a vector. Let's write it as a matrix multiplying a vector x on the other side too. So we can do that by recasting. So we come down here. We recast this equation as a x is equal to lambda I, where I put in the identity matrix. This is an n by n identity matrix. Oops. And times x. Okay. Just to remind you, I has got ones on the diagonal and zeros everywhere else, and it's going to be n by n. Okay. Now what we do is bring these two to the same side. So we have a x minus lambda I x is equal to 0. Now this is not a 0, it's the 0 vector. And now we can write this as a minus lambda I times x is equal to the 0 vector. Okay, let's call this matrix B, this one here. So our equation now is of the form B multiplies x and gives us the 0 vector. Now this will hold true, so solutions. The first case is the trivial one. This will hold true if x is equal to 0. This is called the trivial solution, and frankly we don't care for it. What's the point of it? I mean, we're not interested in this. 3 blue 1 brown calls it the boring solution, if I remember him correctly. Yeah, we don't want that. Okay, so what we want is then a non-trivial solution. And how do we get those? So a non-trivial solution will have x is not the 0 vector. Now if x is not the 0 vector, what does it say about B? Well, let's think about it. If B is non-singular, now what does that mean? I.e. if the determinant of B is not equal to 0, then the inverse of B exists. Okay, remember the inverse does not exist if the determinant is 0. And if you want to remember how, well, you can look at Riley, Hobson and Benz, but basically in defining the inverse we have to divide by the determinant, and if the determinant is 0, then the inverse doesn't exist. Okay, so if the determinant is non-zero, then the inverse exists. So what we can do now is multiply with the inverse on both sides of this equation here. So therefore B inverse times Bx is equal to B inverse times, I don't need the parentheses here, times the 0 vector, which is of course just the 0 vector. Yeah, so here the B inverse can be multiplied by B first. That gives us the identity times x is equal to 0. i.e. that is x is equal to the 0 vector, which is the trivial case. And we are not interested in the trivial case. So for non-trivial solution, and this is important, therefore for a non-trivial solution, we must have mod b, so the determinant of b equals 0, i.e. b, which is equal to a minus lambda I. I'm using a slightly different notation here for the identity instead of this one here, but it's the same thing. This must be singular. Now, it doesn't mean that the matrix A is singular. What's going to happen here is that we are going to, and this is described graphically by 3 blue, 1 brown, so if you haven't watched that video, please do so. What we're going to do is to find out, if you regard this as a function of lambda, it's a matrix now which is a function of lambda, we're going to find out for which lambda can we get this combination of A minus lambda I, for which lambda is this going to be a singular matrix, or for which lambdas. It could be more than one of them, and those are those values for which this matrix will not have an inverse, and it's for those values of lambda that you will get a non-trivial solution for the eigenvector. That's what we're after. So this gives us a route to finding the lambdas. Therefore, to find the lambdas, we solve mod b, which is equal to the modulus of A minus lambda I. Solve this equation, and for those values which satisfy this equation, that is for those values of lambda which give you this determinant to be 0, those will lead to the non-trivial solutions. Okay, so these lambdas will give you the non-trivial solutions. And once we've got the lambdas, so once we know the lambdas, then use A x is equal to lambda x to solve for dx. And this, as we will see, needs to be done for each of the lambdas in turn. I'll show you examples. Okay, so this is what we're going to do. First, use this determinant of A minus lambda I, set this equal to 0. This will give us an nth order polynomial in lambda. We will solve for the lambdas, and then use each of those lambdas in turn in the eigenvalue equation to find the x's, the eigenvectors. Okay, so that's the outline of what we are up to. Let's now use it to find some to solve for some special cases. Now the first case I'm going to look at is the matrix. So case 1. The matrix A is a 2 by 2 matrix. It is 1 minus 1 0 not 0 1 1. Now, okay, so that's A, and what we need to do now is to find the eigenvalues. So now A is 2 by 2, so we will have at the most 2 distinct lambdas, and here's how we're going to find them. So to find the lambdas, we solve this, what's called the secular equation. Now, I haven't said this, but this this equation here is called the secular equation. and this is given by the determinant of a minus lambda I, and that's set to 0. Okay, so that's the determinant of so what is a minus lambda I? That's equal to a, which is 1 minus 1 1 1 minus lambda times the identity 1 0 0 1, and this is simply um, the A matrix, and you subtract off lambdas from the diagonal terms. If you form this, you'll have a 1 minus lambda, then 1 1, sorry, minus 1 here, and then another 1 minus lambda. Okay, so we know what this matrix is, and this is the we need the determinant of this matrix, which is going to be 1 minus lambda squared. That's this term, this product of these two minus the product of those two. So minus 1 times minus 1, which is equal to, let's expand this stuff out. So we're going to get a 1 plus lambda squared minus 2 lambda, and we'll have a plus 1 in other words. So we have lambda squared minus 2 lambda plus 2 is equal to 0. So that's a quadratic, and this is our secular equation. Every year I have students asking me why is it called a secular equation, and every year either you guys find out or I find out, and then I forget about it. So I'm going to put this to you. Go and look it up. Why is this called a secular equation? Because I've forgotten. Right. Or characteristic equation also, I believe. Yeah. Okay. The solutions to this quadratic are quite simple. They are both complex, and the solutions are given by lambda is equal to, if I remember correctly, 1 plus or minus I. Okay. Now I'm going to write. Yeah. So before we go any further, let's just make a couple of observations. You'll see why we make these observations when we look at some more properties of diagonalization. So some observations. One, the trace of A. Let's have a look at the trace of A. It's simply 1 plus 1, that's 2. That's equal to 2. And the sum of the eigenvectors, eigenvalues, sum of the lambda I is equal to 1 plus I, that's the first one, plus 1 minus I, that's the second one, and this is also equal to 2. Hey, they are equal. The second observation is that the determinant of A, which is the same as this, that's equal to, let's say it's 1 times 1, that's 1 minus 1 times minus 1, so it's 2. It just happens to be the same as the trace, but it's not normally the case. And I'd like you to show that the product, this is the symbol for the product of the eigenvalues, is also 2. Is this general? Well, we'll find out in some, well, not in this recording, but in the next one. Okay, so we have these two eigenvalues. What I'm going to do is combine them into one. I'm going to write them as 1 plus epsilon I, where epsilon is equal to either plus 1 or minus 1. Yeah, so it's just a short way of handling both cases simultaneously. You don't have to do this. Alright, so now what we're going to do is find the eigenvectors. So now we have to solve Ax is equal to lambda x. And what I'm going to do is, there are two lambdas here. I'm going to just use them in this form and just choose epsilon to be either +1 or -1 to get both of the solutions in turn. Okay, so what we have then is A is 1, -1, 1, 1. X, well, what is X? We don't know what X is, but I can always call it some vector AB. We've got to find the A's and B's, so we'll call that AB there. And the lambda is here. It's 1 plus epsilon I. And then we have an AB. Alright, so what we need to do now is to write both sides in their vector form. So we have on the left hand side, we've got 1 times A minus B. So the first term is A minus B. The second term is A plus B. That's the left hand side, and that should be equal to the right hand side, and the right hand side is the scalar times each of these. So we'll have 1 plus epsilon I A as the first term, and 1 plus epsilon I B times B as the second term. So we have to have, therefore, A minus B is equal to 1 plus epsilon I times A, and A plus B is equal to 1 plus epsilon I times B. Now I'd leave it to you to show that these two equations are actually the same. So you can choose either one of them. They are the same. You don't get any more information by considering both. So I'm going to look at pick the second one. So from here, therefore, A is equal to, if I bring B on the other side, we get epsilon I times B. And that's the only bit of information you're going to get from these two equations. Okay, so what does that tell us then? Therefore, X is of the form, if I choose B to be something, then A will be epsilon I times B. Okay, or we can pull the B's out, and a 1 there. Now there are two of these X's. Remember, epsilon can be +1 or -1. Alright, so we'll leave it as it is for now, but just keep in mind that there are two of these X's, it's not one. The epsilon, when you put epsilon is equal to +1 here, that corresponds to the eigenvalue lambda is equal to 1 plus I, and if I put epsilon is -1, then that corresponds to the eigenvalue 1 minus I, and then we'll get the second of the eigenvectors. Now question now is, what about B? Does it matter? Well, remember what we said long ago in one of the previous recordings. I said that this eigenvalue equation, here we are, Ax is equal to lambda x. Let's put a box around that since it's an important one. This eigenvalue equation is satisfied for any x. Once you found an eigenvalue x, you can multiply it by any scalar, and you will also have an eigenvalue of A, of the matrix A. So what we do then in practice is we say that we are not interested in any x. We want to use only normalized x. That limits, so in any particular direction, we then limit the eigenvalue to only that vector which is normalized. Okay, so then it's normalization condition which is going to fix what B is. And so we normalize x, and hence we find out what B is. So oops, put that down here. To find B, normalize x. Alright, so remember how we normalize x? We divide it by its norm, and that's given by the square root of the inner product of x with itself. So we need to find out what this is. And if we take the x as we've got it here, in this form, the inner product of x with itself will be x dagger, so let's write it in its alternative form. It's x dagger times x, so dagger there, and this can be written as minus epsilon ib. We have a minus sign because we take the complex conjugate of the vector when we dagger it, and we also transpose it, and then we have a b, that's x dagger times x, which is epsilon ib, the column vector b, and this gives us minus epsilon square I square b square, that's this times this, plus b square, that's that times that. Now epsilon is either plus 1 or minus 1, therefore epsilon square is just 1, I squared is minus 1, so this gives us minus 1 times minus 1, that's plus, so we'll have a 2b squared. Therefore this is equal to x divided by the square root of this, which is b times the square root of 2. And if we now put in our expression for the x vector, we see that the b's cancel off, and we have 1 over the square root of 2 I epsilon 1. That's what our x looks like. So now let's write it down. Therefore, for epsilon is equal to plus 1, lambda 1 is equal to 1, let's remind ourselves, it's 1 plus I plus I, so it's a complex number, and the eigenvector 1 is given by 1 over the square root of 2 plus 1 over here, so we'll have an I, the column vector I 1 times 1 over the square root of 2, which is required for the normalization. And for epsilon is equal to minus 1, the second eigenvalue is 1 minus I, and x2 is equal to 1 over the square root of 2 minus I 1. And we've solved the problem. Now please check it to make sure you've kind of followed all these steps. At the end of any of these exercises, I always, especially at the beginning when I'm doing these for the first time, verify, check to see if this is indeed an eigenvector, these are indeed eigenvectors. Just put it back into the eigen vector equation, which is this one here, and check to see that this equation is satisfied for these choices of lambdas and xi's, and the lambda i's and xi's. Okay, so let's box that. That's the solution. There we are. Now let's say I asked you a question. So here's a kind of something for you to think about. What if I asked you to find the eigenvectors and eigenvalues so find the same for the matrix A dagger. Now you could, of course, you could find it for the matrix A dagger. You take the matrix A dagger, that's the adjoint of A, and you go through the same process for that matrix. On the other hand, what you could realize is that, and I'm going to leave this for you to fill up the gaps, you could realize that A dagger is equal to A dagger A. That is, the matrix A commutes with its adjoint. Therefore, A is normal. And if it's a normal matrix, then you can use the theorems we have proved for a normal matrix. And one of them says that If A is a normal matrix, then A dagger and A share the same eigenvectors, and their eigenvalues are the complex conjugates of each other. In other words, the eigenvectors will be the same, and this is what something I'm going to ask you to check, but their eigenvalues will be the complex conjugates. So the eigenvalues of A dagger will be the complex conjugates of those for A. Now I'd like you to check that and complete this. Okay, so this is one of the kinds of questions which you know ties together different parts of information about this topic, and this is the kind of question which you can expect on the new format of the exams, where I'm going to expect you to think about things, and not go through, not use brute force methods and kind of take A dagger and try and diagonalize it, solve for its eigenvalues and eigenvectors the same way as we've done for the above. Instead, you could use the theorems we have proved and write down the answer in 3 lines. So this is one of those new type questions which I might include. I'm not going to say I'm going to include, but these are the kinds of things which you might expect to see on an exam. In other words, if you've understood what you've done, the answer is simple. If you haven't understood it, you're going to take a long time and make mistakes. Okay, now Riley, Hobson, and Benz have in this section on I think it's here. Yes. So this is section 8.14, determination of the eigenvalues and eigenvectors. In here, they actually look at a 3x3 example, which is something I'd like you to have a look at too. It's a real symmetric matrix. It's a 3x3 example. And what I'd like to talk, and they also have a look at what the degenerate case. So the case where you have a degeneracy in the eigen values. And this is an example. I'm going to talk you through exactly this example, and in fact in the homework set you're going to see another example here, which is slightly more complicated. So what do you do if you have a degenerate set of eigenvalues? Now pause here. All right, back here. So now we are looking at the case for degenerate eigenvalues, and this is an example worked off in Riley, Hobson, and Benz 8.14.1. I encourage you to go to that example and look things over if anything I'm saying is not clear. So here's the matrix. It's a real symmetric matrix, 3x3, and we need to find the eigen values and eigenvectors. Now we proceed as before. So first set up a circular equation, A minus lambda I is the identity matrix. Take the determinant of that, set it to 0. Now since A is 3x3, I must also be 3x3. Okay, so this is 3x3, therefore I is also 3x3. And this gives you the 3x3 determinant, where we have we essentially take the diagonal elements of A and subtract lambda from them. The rest of the terms of A remain the same. This leads to, now you find a determinant using any of the tricks you have learned in your previous courses. One thing I'd like you to think about though is, generally when you're finding the determinant of an exam type question, it will be relatively easy. And in this particular case, if you start to expand the determinant, you will find that the factor of -2 minus lambda appears in both terms, here and here. Now that automatically tells you, you got to pull that term out and then take whatever is remaining inside, in this case, square brackets. And that lets you factorize this thing quite nicely into your factors there. Now what I have seen in some previous examination papers is that students have your predecessors have actually taken this, multiplied it out completely, formed a third order polynomial, and then used long factorization to factor it. And this takes time and it's error prone, and frankly the answer is staring out at you here. So please think about these determinants more carefully when you have to evaluate them, because generally there will be a simple way of doing it. Okay, now Here you get your factorized determinant. This is your factorized characteristic. And what you see easily is that one of the roots is lambda is equal to 4. And the other root is lambda is minus 2, and it's degenerate. There's a square here, so it's degenerate. There are two of those. So we have lambda 1 is equal to 4, and this can be used to find the x1 eigenvector. It's in Riley-Hobson and Benz, but you can easily do it yourself, and I suggest you please do it yourself before checking your answer here. What is of interest here is that the other two eigenvalues are degenerate, and they are both equal to minus 2. So lambda 2 is equal to lambda 3 is equal to minus 2. Now before we go on, let's have our observations once more. The trace of A is 0. That's A. The trace of A is 0. And if you sum up the lambda i's, you get 0. The determinant of A is 16. Please check it. And if you take the product of the lambda i's, you get 16. Oh, this is looking interesting now, and we'll see that in fact this is generally the case. But for that proof, we've got to wait for the next the next recordings. Now here's the question I want to address in this recording is, what about the degenerate eigenvalues lambda 2 is equal to lambda 3 is equal to minus 2? How to find two orthonormal eigenvectors x2 and x3 for this case? And this is what we need to figure out. Yeah. Okay, so how do you go about finding the eigenvectors? What you do is you go back to the eigenvalue equation, Ax is equal to lambda x, and you stick in your lambda. In this case, lambda is equal to minus 2, and then we got to solve for x. Now we don't know what x is, so let's take it to be the form as before, a, b, and it's a 3, length 3, so we'll have a c. Okay, so let's put this in, and let's see what happens here. We need to find two of these x's because we have two lambdas. They just happen to be the same. So let's see if we can actually get two x's. Well, a, let's put down what a is. It's, well, I've forgotten what a is. It's 1, 0, 3. Okay, so we've got 1, 0, 3, 0, minus 2, 0, 3, 0, 1. That's a real symmetric matrix times x, which is a, b, c, and that's equal to lambda, which is minus 2 times a, b, c, and this is just minus 2a, minus 2b, minus 2c. Okay, so let's write down our equations for a, b, and c. We're going to need another page. Let's put that in there and go back down. Okay, so what we're going to get from here is on the left hand side we will have 1 times a, that's a, 0 times b, 3 times c, then we have minus 2b, and then we have 3 times a plus c, and that's equal to minus 2a, minus 2b, minus 2c. Therefore, we have three equations. Actually, it turns out we have only two, but let's write them down. A plus 3c is equal to minus 2a. That's the first equation. Then we have minus 2b is equal to minus 2b. That's a very useful equation, I guess. And then we have 3a plus c is equal to minus 2c. Okay, let's take the first equation and write it down for a. So from the first equation we get 3a plus 3c is equal to 0. Therefore, a is equal to minus c. And if you look at the second equation, the third equation, sorry, it tells you the same thing. A is equal to minus c. So there's no new information here. And all that the second equation says is that b is equal to b, which is, well, not telling you anything at all. So all we know now is that x is of the form if I choose, this also says, by the way, therefore c is equal to minus a, right? So if I keep an a there, then we have b is equal to b, that says nothing, so b stays as it is, and c will be minus a. So x is of the form a, b minus a. And now the question is, what do you do? Because you have two unknowns here. Well, there are a few options we've got. First of all, you could pick any choice of a, b, and c. Now here's where I like to pick the simplest choice, simplest non-trivial choice possible. So first of all, a is equal to 0 is equal to b is equal to 0 is a useless choice. You just get the 0 vector. What if I choose a is equal to 1 and b is equal to 0? So I'm going to put this as possibility 1. We just choose things. I could choose a is equal to 1 and b is equal to 0. What does that give me? That gives me x is equal to, now we haven't normalized x, we'll do that afterwards. X would be equal to 1, 0, minus 1. Let's just compare it to x1, which is what we have from Riley, Hobson, and Benz. x1 is 1, 0, 1. We can forget about the normalization for the time being. And I'd like you to check that with this arbitrary choice of a and b, we get an eigenvector which is actually orthogonal to x1. Please check this. So check that x1 is equal to 0. Okay, now what I can do is call this thing x2. All right, we have to normalize it, and I'm going to normalize it without much affront. So on normalization, x2 would be 1 over the square root of 2, 1, 0, minus 1. Now what about the other? We need two eigenvectors, because there are two eigenvalues which just happen to be degenerate. So I need an x3 from here. Well, let's have a look. I've chosen a is 1 and b is 0. Let's try. So let's try a is 0 and b is 1. And this will give us x is equal to, I was using blue, so let's go back to blue. X is equal to 0, 1, 0. In fact, it's also normalized. This happens to be the case. Now, have a look. I mean, this x is in fact orthogonal to x2 and x1. So we can call this x3, since x3, x1 is 0, and by the way, this follows by definition. Think about it. And x3, x2 also is 0. This second condition doesn't follow by definition, because when we proved the orthogonality of the eigen vectors of a normal matrix, we only were able to prove it that they would be orthogonal to each other if the eigenvalues were distinct. Now here the eigenvalues for x2 and x3 are not distinct, they are the same, so these two vectors don't have to be orthogonal. We have to make them orthogonal. So now we've got a set of 3, x1 which is above, x2 here, and x3 here. Now you might ask, what if you chose something else? What if I chose the first vector to be a1, form it as a1 is 1 and b is also 1. So a is 1 and b is 1. This would give you the vector 1, 1, minus 1. This would be an alright choice for x2. And then what about x3? Well, you'd have to find some vector which was perpendicular to x2. But there's another way of doing it. And in this way, if you think about it, you can form x2 by any choice of a and b, as long as they are, at least one of them is non-zero. And any of those choices would be good x2s. Then you'd have to form x3 by enforcing that x3 is perpendicular to x2. and I'm going to keep this as an exercise for you. So suppose you chose A is 1 and so is B, then x2 would be 1, 1, minus 1. And we'd have to normalize this, and so this is unnormalized. Okay, so what about, so then to find x3, you'd need to enforce x2 being orthogonal to x3. So this should be 0. Okay, we know that x3 is of the form that form is given above. x3 has to be of this form. Think about it. So it has to be of the form a, b minus a. Minus a. Therefore, we must have 0 is equal to the Hermitian, the adjoint of this, which is 1, 1, minus 1, times a, b minus a. And this will give you a condition on a and b. So I'm going to leave this for you. Find a condition on a and b, and hence find x3, and then of course normalize it. So this is your kind of exercise. Yeah, I'm going to put a line there. This is something which I want you to try. But there's another way, which in fact one of your seniors found in an exam, which I was pretty cool to see. There's an even quicker way of finding two orthogonal eigenvectors from here, and here's how it goes. So we know that x is of this form. X is of the form a, b minus a. Let's write it down. So this is another way. Another way to find two eigenvectors. We know that x is equal to a, b minus a. It's of this form. Well, let's write it as in this particular way. We'll have a times a vector, and wherever you see a's, there'll be, so there's a 1 there, then there's a 0 here, and there's a minus 1 here, plus b times another vector, and then we'll have a 0 here, a 1, and a 0. And now you can already see that this vector x is of the form a times a vector plus b times another vector, and these two vectors are orthogonal. So and this is why you can choose, therefore choose a is 1, b is 0, which gives us the first vector, to get x1 is equal to 1, 0, minus 1, and a is 0, b is 1, to give us the second vector, to get x3, sorry, this is x2 here, is equal to 0, 1, 0. And of course you need to normalize this one, so you will get the 1 over square root of 2 when you normalize it. Yeah, and you do need to normalize this, by the way, so I'm going to put this in and this is already normalized. Okay, and in this way we have, therefore, for lambda 2 is equal to minus 2, we have x2 is equal to, let's put the normalization first, 1 over the square root of 2, 1, 0, minus 1, and lambda 3 is equal to minus 2, x3 is equal to 1, sorry, 0, 1, 0. Are these eigenvectors unique? No. This is a non-unique set. So these eigenvectors are not unique. You can find any linear combination of these two will satisfy the conditions for these being, for finding eigenvectors for this particular matrix. And it's up to you to choose one of those combinations. Now, this happens to be the simplest choice. Any other choice will be slightly more complicated. One of those more complicated choices is the one I've put down here as an exercise for you, where x2 is 1, 1, minus 1, and x3 will need to be found by imposing the orthogonality constraint. Yeah. Now, if you choose any A's and B's and you have x1 and x2, what you can then do is use Gram-Schmidt to orthogonalize them. So there are many ways possible. There's always a simple one, and then there are the more complex ones, but there's a well-defined procedure using Gram-Schmidt to solve this particular kind of problem. So I hope I've been able to show you how we handle the case where the eigenvalues are degenerate. There are many ways of finding the eigenvectors even for the degenerate case, and it's up to you to choose something that's nice and simple. So with that, let's go back up here. I finished the recording I finished this kind of short lecture on practicalities of finding eigenvalues and eigenvectors. There will be more in the homework which you will get in class. Thank you for watching.